Guten Tag, guten Morgen, wie auch immer ihr da gerade zeitlich gestellt seid. Ich werde hier ein bisschen was über den Regensburger Marathon-Cluster erzählen, wie wir das Ding ein bisschen reißerisch genannt haben. Es ging dabei um ein Cluster von Maschinen, der zufällig unter NetBSD gelaufen ist, um eine Video-Rendering zu machen, und zwar beim Regensburger Stadtmarathon letztes Jahr hat eine Videokamera den gesamten Zieleinlauf am Ziel jeden Läufer, der eingelaufen ist, gefilmt. Insgesamt 5 Stunden Videomaterial. Wir haben diesen Stream digitalisiert und dann für jeden Läufer, der durchs Ziel gegangen ist, im Endeffekt seinen eigenen persönlichen Zieldurchlauf als MPEG ins Netz gestellt, und er konnte den dann mit Hilfe seiner Startnummer über irgendein Webinterface abfragen. Das war es im Endeffekt. Wir sprechen von 5.500 Läufern, damit 5.500 gerenderten MPEG-Streams. Und ja, ich werde jetzt im Folgenden einfach ein bisschen auf die Technik, die dahinter stand, und das Ganze eingehen. Ja, schon gesagt hier, 5.500 Läufer, die durchs Ziel gelaufen sind. Das ganze Projekt ist zustande gekommen durch eine Kooperation zwischen der Fachhochschule Regensburg, für die ich hier unter anderem arbeite, und der Firma Aircom, lokaler ISP in Regensburg, der sich als Sponsor für den Stadtmarathon beworben hat. Die Aircom wollte das Projekt erst auf ihren 6 Rechnern im Büro machen, haben dann irgendwie gemerkt, die Rechenpower ist vielleicht doch nicht so ganz ausreichend. Wir haben dann persönliche Connections gehabt. Ich habe gesagt, okay, wir haben genug Maschinen, machen wir das bei uns an der Fachhochschule und schauen wir mal. War ein definitiv interessantes Projekt, und also klang am Anfang definitiv interessant, im Nachhinein sowieso. Ja, unterm Strich hat man 45 Maschinen am Ende am Laufen, Ausgang sind wir von 60, warum da ein paar weggefallen sind, komme ich dazu. Ja, ich habe jetzt die Anwendung hier mal Video-Rendering genannt, was genau dahinter steckt, später. Vielleicht auch ganz interessant für die Leute hier, der Ansatz ist 100% auf Open-Source-Software basierend, also nichts Kommerzielles, vielleicht mit dem einen Schritt, das Videoband in ein MPEG zu verwandeln, der wurde auf Windows ausgeführt. Aber hinterher der eigentliche Berechnungsvorgang war 100% Open Source. Die Hardware, die wir zur Verfügung hatten an der Fachhochschule Regensburg, wir hatten 4 öffentlich zugängliche Räume mit Rechnern, mit jeweils 15 Maschinen. Noch Adam Riese 60, ne? 15 von den Maschinen hatten Solaris vorinstalliert, und auf den restlichen Maschinen hatten wir freie Hand zur Betriebssysteminstallation. Die wurden hinterher sowieso wieder platt gemacht. Hardware waren Dell-PCs, teilweise mit 500 MHz, teilweise mit Gigahertz. Ja, nicht mehr ganz zeitgemäß, das Ganze ist auch schon ein bisschen her. An Software diverse Komponenten. Als erstes das Betriebssystem selber auf den Cluster-Nodes NetBSD. Warum? Zum einen mal, NetBSD läuft einfach auf den Dell-Optiplex-Dingern ohne Probleme. Es war auch ohne Probleme ihn zu installieren, und ja, wir hatten einfach im Haus auch einen Haufen Erfahrung, Know-how mit dem Betriebssystem. Ansonsten auch die Software, die wir für den Cluster benutzt haben, ist in der Third-Party-Collection von NetBSD ohne Probleme verfügbar. Man musste da nicht irgendwie groß Software per Hand installieren. Jetzt fällt mir gerade was zwischendurch auf. Frage. Ich rede hier Deutsch, die Slides sind in Englisch. Is anyone here speaking English and does not understand me? Yeah, okay, sorry for speaking German. I was not aware, I'm a bit tired. I will switch over to English if that's okay with you. The policy for the CCC camp was to talk in English if the presentation was announced in English, and to talk in German when it's German, and I didn't pay enough attention to the language, so I will continue in English. Sorry for that. Okay, so node operation system of the cluster nodes was NetBSD. The software we used for the video rendering cluster was dump MPEG and MPEG encode, and various graphics libraries which they use. Also, for monitoring purpose, we use tload, the UCD SNMP implementation, as well as the stat daemon. For deployment of the cluster machines, we use the G4U disk image cloning software. This image, yeah, fits on the screen, displays how we got to install 50 machines. I mean, the approach we took was we did set up one master deployment server, installed NetBSD on it, installed all the application software we needed on it, all the video rendering, clustering software, and also configured it in a way so we were able to clone it, so no fixed IP addresses, use DHCP and such things. We made a disk image for that using G4U, and then from the master deployment server, we installed 3 PCs, one in each of the rooms that we had. Remember the fourth room had Solaris pre-installed. So in each of the rooms we had then one server running, which we again set up as room server. Just make it a FTP server and that's it. It's very easy with G4U. And from these room servers, we went into installing the remaining machines in that room. We took this two-step approach because there was a router in between the first and second step, and we wanted to have full speed for installing many clients, so we installed these room servers in between and then from them. After installing the cluster nodes, well, this is the task that we did in the whole job. Let's go from left to right. The preparations we had on the very left, the camera filming all the runners going through the goal and reaching it. We had a videotape of that. Well, actually not one videotape, but 4 or 5, I don't know. It was 5 hours of video stream. And we used some Windows PC for some reason to make an MPEG stream of this video material. We also split the very long MPEG stream of 5 hours into several shorter sequences of about 15 minutes or 12 minutes or so, and put them on CD for easy distribution. We didn't want to use network for some reason. Must have involved a problem with Windows. So we had a lot of chunks of MPEG streams, and then we cut these chunks of MPEG streams into single images. This was the first task that the cluster did, splitting up the MPEG stream into pictures, into single pictures. After that, with some step in between, the second step was to calculate the 5,500 single videos showing each individual runner reaching the goal, and then, yeah, assemble these images again. So rendering 5,500 videos of length of 6 seconds each. Well, yeah, and that was the result. 5,500 videos, and also we had images of the runner reaching the goal at that exact moment, so still picture for printing or something. And as a result, we put some web interface to them, and they were able to view the videos and images. So let's go into the first task that the cluster did. It was splitting the MPEG sequences. We had 11 minutes per sequence of MPEG stream, and these 11 minutes resulted in about 16,000 single images. The time it took us was about 45 minutes on the fast 1 gigahertz machines that we had. The software that we used was Dump MPEG. This is an open source software, of course. It uses STL and some other software. We had some interesting effects with DumpEG. First one was the program writes BMP format by default. This has 2 implications. In the second step, we needed JPEGs for reassembling the JPEGs into MPEG. And also, as you probably know, from storing things, a BMP is much bigger than a JPEG. So, and we didn't have infinite disk space either, so we had to do something about it. We wanted BMP. The problem was there was no JPEG. We wanted JPEG, of course. There was no JPEG writing routines in the STL and SMPEG libraries that dump MPEG uses. Using a manual approach. We hacked the source code of dump MPEG. It's a good thing with open source software, you can change it and fit your needs. We hacked the tool to just call the NetPBM tools to do a BMP to JPEG conversion. To be a bit more efficient, we did this after writing 250 BMPs to disk and then do a batch conversion JPEG, so to avoid a little bit of fork and exec overhead. Of course, it would have been nice to replace more of these cores as they are very expensive, but we didn't find any JPEG writing libraries, so this wasn't implemented at that time. For also improving access times, we also placed 250 images each in their own directory, so to improve directory access and file access. Well, after we cut down the big MPEG stream into single pictures, I already mentioned that we put the big stream into smaller streams to distribute it on many machines first, and then let them write the single images. The point was we had to find exactly an image for a given time. When we know some runner reached the goal at a certain time, we have to find the definite image for that time. And now there's a problem, because when you start calculating, you assume we have 25 pictures per second, and then say, okay, we have from the start of the video, we have 25 pictures per second, like 60 seconds an hour, 60 minutes an hour, and then the runner reached like 4 hours in the past or in the future. So you can calculate how many images you have to skip. The problem is this does not work, because there is not always a frame rate of 25 seconds from the video input we had due to some thermal effects, and which resulted in many mechanical inaccuracies. So we already expected this, and watching the results a bit, there was a wall clock also on the image of the videos, so we could check which time was on which sequence. And then as a result, we recorded time of first picture and time of last picture for each of the sequences, and recorded this into some database, so we could say if you need some time, it's in this or that sequence, and then start counting from the start of this sequence, assuming 25 frames a second. And this usually worked quite well. If you didn't do it like a small difference in the timing, it could have added up to an unusable result over 5 hours of the material, which we did not want to risk. Also, maybe let me add it. This wasn't really tested before. It was a one-shot calculation that we did. We had some company develop the software or hack on the scripts rather, and then just make a really short test run, and then we actually got to the marathon, and the same day we started rendering the images, so there was no time for actually testing the whole setup. This was done on the living victim. Okay, after we had the single images for each sequence, we were able to again merge them into the videos for each runner. We had 5,500 runners which reached the goal out of about 7,000 people starting altogether. In the marathon, there were 3 disciplines. The full marathon was 42 kilometers, a half marathon was 21 kilometers, and also speed skating, rollerblading, with over a distance of 21 kilometers. The list of results were kept separate for women and men. So about 6 lists of results. And yeah, the image selection that we did. We knew the time of when the goal was reached. This is the red line on this. So to select the images, we back. We selected 150 frames. That's 6 seconds of video input. We took then these 150 frames and also at the end added some credit frames showing sponsors' names and name of the runner, the rank he got and things. This resulted in a video length and full video length of 156 images, 156 frames. These frames were then copied to a working directory for rendering this individual image, video, sorry. A word about the credit frame. On the left you see a blank template that we used. On the right you can see a full template, the name, starting number, time and discipline and place. This was added automatically using image magic. And we also did that based on the list of results and automating this for the credit frame. Besides doing the videos, the images, we also had a still picture of the runner reaching the goal. You can see him here on the right side in the picture. And we also added some text on the lower left so he can print it out or something. This picture was also archived for retrieving then for the web interface. Okay, the rendering itself was done with using the MPEG encode program. This is a very fine piece of software. It's free, and it does all the rendering for the video itself. It first sends a few images to each of the machines that you say are available for rendering. Then it estimates the speed of those machines, so it knows how fast they are. After that, it distributes the remaining images accordingly to the speed of these machines, doing equal load balancing. The images are read by the cluster clients from NFS storage, and also the resulting video parts are written back to NFS storage by the cluster nodes. The main master MPEG encode process then collects and merges the video parts at the end. So this is really load balancing over a given number of machines that MPEG encode does here. It just works. Can't say much more about that. It's doing a really fine job there. So this is an overview of the thing we did in the end. It shows the 3 rooms that we had. Oh, yeah, one more thing. This shows 3 rooms. I mentioned 4 initially. It's not mentioned yet, but we lost one full room, all the Solaris machines, because we had some software problems in there. I will tell you about that later. So in the end, we had 3 rooms with machines only, and all they ran NetBSD only. So this is an overview of the 3 rooms, one on the upper right, one on the upper left, and one on the lower left. The one on the upper right had a fast machines with 1 gigahertz, and both on the left side had a rather slow 500 megahertz CPUs. Then we divided this into several subclusters for more optimizations, and there are also 2 machines for controlling the cluster. One which was running Red Hat for just issuing out the jobs. This was no particular reason for Linux either, but we happen to have it. The other machine, quite important one, it was a Sun machine running as central NFS storage, storing all the images and also for transferring the videos and parts of them. So as we have split the available machines into the 4 subclusters, we needed several MPEG encode config files for each subcluster too, and needed to fix our scripts. After that, well, what we had as input for the whole thing was list of results available as CSV file, column separated values from some Excel Windows thing, which contained the name, the place, and the time of the runner. And for each runner, then we started calculating. Prepare the working directory with the 156 images, render the video, store the video, and also store the images for 5,500 times. One other thing, MPEG encode uses remote shell, not secure shell, for accessing the cluster nodes, and we use remote shell on purpose because to prevent authentication overhead. If you look at it, rendering one of the MPEGs was between 3 and 8 seconds. Looking at SSH authentication, it takes 2 seconds. 2 seconds that we really didn't want to invest. So cut down secure shell, use remote shell. It worked fine in our environment. There were no security considerations to have, so nothing to lose there. And yeah, this was really just a loop over all the results. As I said, render all the videos. And in the end, we had a directory with 5,500 videos and images. We put some web front end over that, and the runners were able to view their individual videos from that web interface, then from their home PC. And well, the whole thing took us about from Sunday afternoon when the marathon finished, for us starting to process the videotapes into MPEG and then going on to splitting the MPEG and then calculating all the images. We started on Sunday afternoon at about 4 in the afternoon, and the whole job of calculating these things was done on Monday, 10 in the morning. Of course, we worked all night, but we wanted to have the results of the marathon available as soon as possible. And yeah, the whole thing also gave us a lot of experiences that I would like to share with you. First one was the deployment of the client workstations of the cluster nodes. Took us longer than expected. Next one was that dump MPEG had some problems on Solaris. It also ran longer than expected. We had to find out that MPEG encode doesn't scale infinitely, and also it just sometimes hangs for some reason. I'll go into details of these a bit more. First was experiences while deploying the cluster nodes. We use a disk image-based cloning system, G4U, and the image had a size of about 650 megabytes, which we then deployed over the network. Deployment of one image took about 30 minutes for setting up the room servers, and when estimating again, like 30 more minutes to have the whole thing done. This was wrong because deployment of the 11 or 40 machines from one room server to the remaining machines of the room took rather long, more than 2 hours compared to half an hour before. This was due to many machines fighting over network bandwidth and also disk I/O on the setup server, because it was reading that 650 megabyte file for like 10 processes or so. And this made the whole process rather slow. Also, all the cluster nodes, all of them, were connected to the same switch, all 3 rooms. And a possible improvement for this in the future, if we ever do it again, would be to use 1 switch per room. Of course, that needs hardware first. Next experience we made was well, dump MPEG and Solaris. Dump MPEG worked fine on NetBSD and Linux, but it sporadically dumped core on Solaris. Let me add a word how we got into this thing. We at the Fachhochschule Regensburg just did the machine system setup and maintenance, and the people at Arcom developed the whole cluster rendering system. And they just then used our machines to do it. The thing is, they got enough test accounts using NetBSD and Solaris so they could fix the software if problems arise. They used Linux for testing only. This was the problem. They didn't test on NetBSD, they didn't test on Solaris, and the result was properly, or not tested properly. When we found out in the evening before the whole event, we started poking around with GNU debugger, which then showed some crashes in the malloc memory allocation routines. We could only guess that it was overwriting some memory, and that Solaris takes overwriting buffers more serious than NetBSD and Linux. But this didn't really help us, so overnight we lost 15 machines for the whole cluster, which was rather bad. In retrospect, there is a library libbsd malloc in Solaris, which would have probably helped us because it implements different memory allocation schema, and which would have been probably better for our type of applications. We didn't know about this library before, unfortunately. So the thing that we learned from this is really, with more time and testing on the real target platform, this could have been avoided. The people who implemented the software just used Linux, and well, not all the world is Linux. This is what you can take home from this. So after getting dump MPIG going, and then next experience we had to make it was slower than expected. We had a test sequence of about 18 minutes length, and it took us about 60 minutes to split on our fast machines. So for the 12 machines running through the 5 hours of video input, we estimated 8 hours of them running, or to take 5 hours. In reality, we had to find out the machine take 8 hours. One reason here would probably be related to disk I/O on the local disk, and also to NFS storage and network load, because all the 12 machines or so were writing to central NFS storage concurrently, and this was probably the main problem here. So the next experience we made when reassembling the images into MPEGs, sorry, was that the sequence of 156 images cannot be computed on more than about 15 machines. This is like you need something to hand out first to estimate machine speed, and then there is nothing much left, so you can't do this with more machines. MPEG encode really just refuses to work in that case. So we had 45 machines available, but couldn't really use that. As a result, we had to split the available machines into the several subclusters that you saw before, 4 of them. So we also had to adjust config files and handling scripts, and scaling was also done using one list of results for each subcluster, and the scheduling of which list ran on which subcluster was done manually. Just see where it is and hand it out to the subcluster in question. While doing the calculation, we had to find out that MPEG encode sometimes just hangs. After printing some text, it sits there and does nothing at all. We did some quick debugging or code inspection of the source code, which we fortunately had, but there was nothing obvious happening, so we didn't know what to do and implemented the usual workout. Control-C it, stop it, then edit the list of programmers or of runners that we already processed, so we don't render things duplicated, and then restart the whole subcluster in question. This was a manual approach, but we didn't find anything better in that time. Yeah. Maybe some stats about the whole thing. We had some MRTG graphs for the whole event. The upper one is disk utilization of the NFS server. I don't have a pointer here. You can see It's starting at about 16 o'clock and ending at about 10 o'clock in the morning. The two cluster steps can be viewed here. The blue ones is when writes happen to the NFS server. This was when the images were written, actually reading them back from the cluster nodes, and writing the MPEGs wasn't really that much volume, so this doesn't show up. It's mostly reading images in the second step of the cluster, shown as green here. You'll also see that there is some overlap between the first and second step. This was because the speed skaters were done very early, and when we had all their data for images, we were able to start calculating them before the last runner reached the goal for splitting, of course. The lower image here displays the network traffic between the cluster machines and the control machines, where what you can see here is mostly the setup of the cluster nodes from some Saturday even in the evening, about, 18 p.m. to 10 p.m. And then this is the start of the cluster working. It's just, well, shows some activity, and there was nothing more going on during the night. We did also some load monitoring on all the cluster nodes. This is again 3 rooms on the upper right, upper left and lower left. And the yellow numbers, you can't read them here, are the 4 subclusters. The upper right room was divided into 2 subclusters. And, well, this is the system load or load average while doing the first step of the cluster while splitting the images. We only did this on the fast machines with 1 gigahertz, so you can see quite some load in the upper right corner, and the remaining machines were mostly idle at that time. This changed when we put the runner into the second step, and at that time all the machines that we had online started going and, well, got some load. The program that we used to do this was not Xload, Xmeter. This Unix program. It uses the stat daemon for retrieving load and things. Maybe a few numbers to give you an impression. Well, we had 5,501 participants. In the beginning, we had available of 57 computers. In the beginning, we had to drop out of Solaris. Also, at least one dropout due to a broken floppy drive that we couldn't install NetBSD on it, and so on. The running time of the videotape was 5 hours, and this resulted in more than 600,000 single images after step 1, which took about 17 gigabytes of disk space. Average image size was about 27 kilobytes. Average size of a resulting video was about 1 megabyte. So as a result, this gave us 150 megabytes of image data for still images, and an overall video volume of 5.5 gigabytes, which we had to carry to our ISP first, using really manually carrying the computer. We didn't, at 10 in the morning, we didn't want to start pushing over 5 gigabytes over some slow line, and really just took the machine and carried it there. So let's sum up the software that we used in the whole process. Dump MPEG was used for splitting the images into JPEGs, and MPEG encode was then used to render MPEGs back from JPEGs. SDL and SMPEG, also as well as NetPBM, were used for dump MPEG as dependencies. We used Perl, GIMP, and ImageMagick for various image processing and scripting things. Tload and Xmeter were used for node monitoring the images that you saw before. The G4U program was used to install all the 50 machines, or yeah, almost 50. And well, all of them ran the NetBSD operating system as operating system of the cluster clients. The whole team that was participating in the event was 8 people. It consisted of students of the Fachhochschule Regensburg, which helped in setting up the machines, and also a team from the, mostly me from the Fachhochschule Regensburg for maintaining setup and system maintenance. Yeah. Well, so much about an overview of our video rendering cluster using NetBSD. If anyone has questions, so I'd like to answer them. If not, thank you very much. Du hattest eine Frage? You had a question?
Okay, what kind of source material did you have? So did you have a DV cam, or did you have just a normal camcorder?
Does this work? Yes. The input material we had was videotapes in Sony Betacam format. This is something used especially for video and TV companies. We were working together with a TV company here, and they also had the cameras. We had 2 cameras actually filming the go, because you have to have some overlap when changing tapes. The tapes have about 2 hours or so, and we used 2 cameras for filming the thing, and they gave us a recorder for displaying and Sony Betacam images. This was saved because the quality of this is better than any VHS system or so. Okay.
In what kind of resolution did you send out the pictures and video?
This is a good question. I don't know. We used the standard MPEG-1 resolution, which is not too much. It's about 300 or 400 images by 200 or 300 images pixels. It's not too good resolution actually.
As far as I understand it, you used Intel-compatible hardware exclusively. And well, one interesting thing about NetBSD is that it runs on so many platforms, especially older vintage hardware and stuff, which may be available at no or little cost. Do you think it is possible to build a cross-platform cluster, and do you think it is possible to integrate older machines like DAC stations, etc., or would it be too slow to run such a cluster?
It wouldn't be too slow and would definitely work. The problem is you have to first get the hardware and then install it, and this is the main problem. We had 1 image prepared for the PCs, which we put on all of them. They had different memory configuration, they had different disk layout, and still the 1 image for deployment was enough. And if you start having different kinds of hardware, doing the system setup is really hard, and we didn't want to go into that. Also, we also had that hardware available, and we didn't actually buy the computers for this task. So in theory, it's no problem. You just need the MPEG encode binary to do the actual video rendering. And this runs on really every platform. And of course, you can also integrate slower platforms, because MPEG encode does this nice load balancing, testing each node how fast it is at first, and then doing the actual rendering. So you can, of course, really integrate a WAX using NetBSD or something into such a cluster. It wouldn't have been a problem at all. But really, it's a question of cost of setting the system up. Anyone else? Yeah. Any other questions? No? Okay. Okay, then I'd like to thank you.